Hello and welcome to the design video for the autonomous torque robot, or ATR as it will be referred to throughout the video. Raytheon currently uses manual labor to torque fasteners that requires multiple tools and employees. This is an extremely time-consuming and labor-intensive process that can involve human error. Our team will be developing an autonomous torque robot for Raytheon missile systems in order to reduce manual torquing labor and increase overall assembly quality. The ATR needs to be a working prototype that will be able to fasten two different types of fasteners, each with two different sizes, onto a flat test plate. These fasteners will have an asymmetrical orientation on the test plate. Therefore, a robust graphical user interface, or GUI, is required so that the user can enter their desired torque pattern and torque values into a computer. User entry locations for fasteners may not be exact, therefore an optical positioning system will be needed to accommodate for predefined fastener location tolerances. Movement will be autonomous and utilize a gantry rail system, just like many computerized numerical control, or CNC, routers used today. The ATR will be able to store the torque values of each fastener for quality control.
The first challenge of the problem was figuring out how to achieve a wide range of torque values. To hit the highest torque value, the team decided on a gearbox with a small motor to achieve the 30 foot-pounds of torque needed. Researching different ways of limiting the torque output of the motor to achieve the variability was the next phase of the project. Different methods were analyzed to provide the best option, which was a torque sensor that would stop the motor when a specific value was reached. This option also allowed for the torque to be read and recorded for a requirement of printing a data collection for quality control. The next was finding a cost-effective gantry system that would handle the torque of the motor and handle the positioning accuracy requirement. Researching into gantry movement, threaded rods were not allowed by the sponsor's request except on the head of the gantry for rigidity. Therefore, the best option was a belt-driven gantry that allowed for precision movement well above what the product needed. The hardest challenge was figuring out how to position the gantry head and mesh with the bolt. We have been testing cameras for the position correction if the bolt is off of its true position to be able to adjust the coordinate in order to mesh. The last step was getting many softwares used to talk to one another and send code back and forth for the correction for the autonomous portion of work.
The major requirements that drove our design were that the ATR shall torque fasteners within a range of 50 inch-pounds to 30 foot-pounds, be capable of torquing 1/4 and 5/16 inch Torx and Allen head fasteners, have torque accuracy of plus or minus 10%, include a GUI to allow for user setup, interface to a rail system for movement, be powered from standard wall outlets, and output a file for production quality assurance.
Now we will be moving on to our design concept and chosen point designs. There are several components that were going to be critical in completing our system requirements. First off, the gantry system. Through our research, we concluded that buying an off-the-shelf CNC gantry would be not only less labor-intensive, but also more cost-effective. We decided on a product called the Work B1000 by 1000. It is belt-driven on the X and Y axes with the lead screw position on the Z axis. The system came with a power supply and control box. Moving on to the torque sensor. In our design, it's used for quality control and also to stop the motor at the correct torque. It is difficult to find a torque sensor that could cover a large range, be accurate, and fit within our budget. We found a reaction-style torque sensor that met our requirements from a company called Transducer Techniques. The only complication with this choice of a reaction-style torque sensor is the wire would wrap around the torque driver assembly because it is connected to the motor output. But this was solved by adding an electronic slip ring to the assembly. In order to reach the max required torque value of 30 pound-feet, a planetary gearbox made the most sense because we were going to require a large gear ratio in order to use a reasonably sized motor. We found a solution at Bex Robotics with their Versa planetary gearbox. A 200-to-1 gear ratio allows the gearbox to sustain its max efficiency throughout the desired torque range. In order to ensure that no downward force was being put into the plate when the torque procedure was taking place and ensure a small buffer of safety from crashing the tool head, we designed a spring-loaded coupler with 1 inch of linear travel. With our design, we can lower to a set height so that the coupler is compressed about 1/2 inch, start the tool head, then mesh with and fasten the bolt to the required torque without moving from the initial set height. It uses a cap with reverse threads and a square hole to transfer torque to a socket extension that is ground to have 4 flat sides. The cameras were chosen because of their size, high resolution, autofocus ability, and software capability. A LED ring was used to control illumination levels at the bolt to reduce shadows. The image processing programs were written in MATLAB.
For the system verification of a few driver requirements, we were not able to complete the test for the torque range and accuracy due to COVID-19. However, we were able to complete a movement accuracy test and test our GUI to be able to input torque values and print out a data collection sheet, as well as test our optics and software communication. The test for the torque was going to be done at Raytheon metrology facility using their calibrated torque sensors. We created a stationary gantry to be placed over the test sensor so it would simulate the machine meshing with a bolt. This would have tested the accuracy of our readings from the torque sensor and our ability to hit a specified torque. The gantry movement test was done by measuring the position of movement by hand while code was run to move the gantry 0.1 inches over 100 1,000ths of an inch increments. This was to provide evidence that the gantry moved actually enough to position at any point around the requirement of the 50,000th inch tolerance. The test for the optical system was set up by importing images of the bolt and tool head from a camera to a MATLAB program. An offset was induced within the 50,000th inch true position tolerance in some images, and a picture was taken at approximately the same field of view where the camera is actually mounted. For the software control test, a simple test was set up to show that the many different software programs could work together and move the gantry system. A G-code file was created from the GUI and put into OpenBuild's control software and was capable of running the machine in the exact order of inputs from the GUI. This will be shown in a demonstration later.
Our results consist of testing the accuracy of the optical position system and the degree of automation of the software. The optical system used an LED ring for illumination, which eliminated shadows in the image. The captured image was processed to find the torque bit and bolt offset. The system had relatively small errors limited by the resolution of the picture. For this test, fractions of a degree of error were found, and the largest error in position was 8% of the 50,000th tolerance value. The GUI was written in Python and has locations to enter the properties for the bolts, such as size, number, desired torque value, and their positions. The Python software is able to convert the bolt positions into G-code to be used with the gantry and called the MATLAB image processing program. The Python software can autonomously run the Arduino Mega 2560 and receive serial data from the Arduino, such as the torque data shown on the right for quality control. Here's an image of the gantry system, which can be controlled through the GUI.
Deliverables to our customer were supposed to include a working prototype, but due to the COVID-19 outbreak, we were unable to complete assembly of the ATR. Therefore, final deliverables will be a final report and technical data package that explain the design, testing, and operating procedures, as well as a software package that includes our GUI, Arduino code, and MATLAB software.
To demonstrate the ATR, here is a clip of the gantry system movement in the X, Y, and Z axes directed by a G-code file written by the GUI. The user inputs bolt locations and the GUI automates the movement of the gantry system. This video shows the potential movement speed while achieving a resolution of 1,000th of an inch. During operation, the torque driver would approach a bolt location. Due to manufacturing tolerances, the optical system would activate and take a picture and process it to measure the bit and bolt offset, and the G-code will be updated to reposition to be directly over the bolt head. The torque driver would begin rotating while lowering simultaneously. Once contact is made, the spring-loaded coupler would compress until the bit and bolt meshed.
One of the biggest surprises we had during this project was when we took our initial spring-loaded coupler design, shown on the left, to the machine shop and we got our quote back. It was way more than anyone anticipated and was 2 to 3 times over our budget. We did not take machinability as a factor in our design process. The material selected, 1566 high carbon tool steel, along with the chosen features meant that the part was going to take many hours to machine, which was driving the cost. The new spring-loaded coupler design, shown on the right, required less steps, had easier to machine features, and was made of a softer material, 1060 low carbon steel. All of these factors helped to decrease the price and time required to manufacture the spring-loaded coupler.